we're ready to go. I'd like to go ahead and get started with our TAG meeting. It's great to be back. It's been about a decade since we've worked together on the treated wood issue, and it's good to see familiar faces and new faces in the audience. And thank you all on the phone and also all who are here in person. We will introduce ourselves so that everybody on the phone knows who's here, and then everyone on the phone will also introduce themselves. So what I will do is I will, on the next slide, we'll do our introductions for everyone in the audience. I know just about most of you. I'm Helena Solo-Gabriel. I'm a professor at the University of Miami, and I'm joined by two students, Athena and Juniper, who will be presenting as well. Do you want to say a few words, Athena and Juniper?
Sure.
Wait, we have, yes. Then we can have this. If you want to come up. If you want to come up, because we are using a mic to help us with our audio here.
Yes, hello everyone. My name is Athena Jones, and I'm a senior in environmental engineering at the University of Miami. We just started working on this project, Juniper and I, so we're very excited to get your feedback on what we've been working on so far.
And we'll probably learn way more from you guys than anything that we've looked at. But my name is Juniper, and I'm also a senior, and I'm doing environmental engineering from the University of Miami, and welcome.
And Tim Townsend, would you like to introduce yourself? Tim?
Hi, I'm Tim Townsend, professor of environmental engineering, University of Florida. And Kim Strickland is a PhD student here. She's going to present. And then Ryan is one of our undergraduate students. He's here to learn.
And Ryan is, okay, well, we'll introduce you when you come in. And if someone can help me with the camera, because we want to record myself with the camera so that people can see me on the webcam. But it's not recording.
I think so.
Yes. Can you see us on the webcam? Or is it only a sign? You only see the screen.
Hey, I just want to confirm, you guys, my microphone is working. Can anybody hear me? It's Rick from Austin AI.
Yes, we hear you, Rick.
Oh, good, good. I'm not sharing my video. I just came back from running.
Okay. Yeah, I know I may overload it. I'm lucky to have it.
What about that gray icon there with the camera? Did you touch that, select it?
Cash also, no. I don't know.
This.
Oh, this. Ah, that camera.
Yes. The webcam is not available.
Oh, sorry. Can you see me on the screen? Can you see me on the webcam? Okay, perfect.
So it's good.
Thank you so much. Thank you. Thank you, Danny.
You're welcome.
Okay, I'm hoping we got over our technical difficulties. And let's go ahead and get started on introductions.
Technology, huh?
I
Isn't that
know. I've got the webcam working now, but now
This is what we don't want to do.
okay, finally, I got the meeting going, and so we've got our TAG members that will introduce themselves. We can go with Gene, who's on the line. Can you unmute yourself?
Hi, this is Gene Advincula. I'm Sales Director of Florida Wood Recycling. We're a facility in Dade County that specializes in sorting out wood, picking out what's recyclable, We take in metals, we take in plastic, cardboard, we have a MRF, we process materials and recover, according to our report every year with the FDEP, 84% that goes through the facility is recycled.
Great, thank you, Gene. Is Frank Bermudez on the line? Now we have Fernando in the audience, who is representing IRC Recyclers.
Hi, good morning, everybody. My name is Fernando Sartor. I'm representing Indian River County Recyclers, which is a MRF facility, which we recycle about 80% of everything that comes in, from wood, cardboard, paper, metal, plastics. Pretty much 80% of all materials coming in will get recycled.
Danny Kreiser, would you like to introduce yourself?
Hello, my name is Danny Kreiser with East Coast Recycling from St. Lucie County. I've been in this industry since 1991, and I've been trying to help these regulators and researchers ever since. Thank you.
Michael?
Yeah, Michael Bland, I'm a PG with solid waste section with the EP in Tallahassee doing permitting, and I'm one of the regulators he's trying to.
I'm here to help.
Thank you. We appreciate it.
Lee Casey, you're on the line?
I'm on the line. I'm Lee Casey from Miami-Dade County Public Works and Waste Management. I oversee our waste energy plant. We produce about 250,000 tons a year of fuel out of clean yard waste for export to the sugar boilers.
Is Himanshu on the line? David, are you on the line?
Yeah, I am Thabit Tolimat with the U.S. EPA, Office of Research and Development, and this is a kind of a deja vu for me. I remember I was one of the students more than 10 years ago, I think 15 years ago or so, was one of the first graduates. Oh yeah, thank you.
Good job.
I don't look as good, let's just say that, but I was one of the first graduate students working on the CCA project with both Tim and Helena. I'm very honored that they have asked me to serve on this group. So hopefully I will be able to assist with the research somehow.
Thank you, David.
And oh yeah, by the way, one comment for Tim. Fortunately for you, you don't have to listen to the Life of a Tree presentation again.
Thank you.
That was the title of my first presentation.
I like that presentation.
Thank you.
David D. Is not able to join us. Kelly Russell was going to join us a little late. Kelly, by any chance? I don't think she's on the line yet. Tomei Tuttle, I have not heard from. That brings us to Kevin Archer. Michael Collins is here in person.
Hello, my name is Michael Collins. I'm with Lonza, or Archwood Protection. We're a supplier of CCA.
Thank you. Thank you. Thank you for being here. Representing Coppers is Charles Shaw, or Chuck Shaw.
Yeah, hi everybody. I'm Chuck Shaw with Koppers Performance Chemicals. Basically, we're the division of Koppers, formerly known as Osmos. We deal with most waterborne, or we sell waterborne preservatives. I'm heavily involved in regulatory and industry activities, particularly regarding our industrial products, i.e. CCA. So glad to be here.
Thank you. Keith?
Yes, this is Keith.
Oh, I'm sorry, I'm out of order. I'm sorry, I was looking at the wrong list, but go ahead, Keith.
This is Keith Weitz from RTI International. I've been doing wood waste management research with Helena, Thabit, and Tim.
Thank you. Jim Healy.
Yes, I'm on the phone. Jim Healy from Cox Industries. We are a major wood treater of both residential products and utility poles using CCA, DCA, TENA, and fire retardants.
Kevin, Jim Hickman, I don't think is on the line, correct?
Hey, Kevin Reagan. Yeah.
Jim is not.
Kevin Reagan, Southern Pressure Treaters Association. We're an association that represents the industrial wood treaters, which we utility poles, cross arms, posts, and pilings.
Thank you for joining us. Stan?
Yes, Lebo with the USDA Forest Service Forest Products Lab in Madison, Wisconsin. We do research on various aspects of wood durability and making wood products, structural wood products, last longer when used outdoors.
Rick? Rick, I know you're on the line because you just introduced yourself a while ago. Okay, you must be on mute. When you find the mute button, just let us know. Keith introduced himself. John Sheriff just arrived.
Hey, what are we saying?
Introduce yourself.
Oh, hi, I'm John Sheriff. We can blame Bill Hinckley for all this. And I'm wearing my original Florida Power and Light shirt. Remember these things? That's dated.
Yeah.
So we're so happy to be involved with this one. Thank you. And somebody told me once that getting professionals to work together is like herding cats, but that's not true with these two people. They really work well together. Best collaboration you've ever seen.
I'm Tim Benson with the Hinckley Center. And John and I were the only ones from the Hinckley Center here today for this one.
Hi everybody, I'm Ryan Richmond. I'm a fourth year environmental engineering student at the University of Florida, and this is my first semester with Dr. Townsend.
Hi, I'm Dr. Joy Bress. I just recently graduated from College Science and I'm researchers in the area of residential contamination with CCA.
Whoops.
God, it was empty.
Too many cables. Well, thank you, everyone. We have a great group. Bo Bruner was not able to join us, and sends his apologies. Okay. The camera, I don't know if you can see the camera or I need to be able to see the slides, and I don't know how to set this up. So, okay, I don't know how well the camera's going to work. We'll do our best, but I'm going to go ahead with the presentation. You should be able to see the slides. And during this presentation, we're going to talk a little bit about the history of treated wood research. We're also going to talk about the types of treated wood. We're going to get into the motivation for our study in 2015, and then discuss the research objectives and approach. Okay, so starting with the history of the treated wood research. This project started out as a wood disposal issue. In particular, back in 1995, there were large wood cogeneration plants in the state of Florida that would burn the gas, the vegetative byproduct of sugarcane manufacture, to produce heat and energy. And this operation was very beneficial from the point of view of recycling, because not only did they use a waste product to produce energy, but they also took that ash and land applied it as a soil conditioner for their fields. And so it was a win-win type operation. Then they expanded their operation and started accepting wood waste from other sources, including recycled C&D wood. They also applied, they generated energy from that, and they applied to land apply that as well. And they were required to test it when they were going to, before they land applied it. And to everyone's surprise, at that time, there was elevated levels of arsenic and chromium. And at that point in time, we didn't know, I mean, it was sort of, where is this coming from? We didn't realize that there would be in recycled wood waste arsenic and chromium. And so that led to the project on CCA treated wood, because we thought at that time, okay, well maybe it is CCA, but is there enough CCA to really account for what we're seeing in these huge cogeneration plants? So what is CCA treated wood? At that point in time, we were learning what CCA treated wood is, and we do believe that it was the cause of the elevated arsenic concentrations in the bagasse from the sugarcane manufacturing facilities, the energy produced from them. And again, CCA stands for chromated copper arsenate. Any wood that's used outdoors typically is treated, has to be treated to protect it against fungi and also insect attacks such as termites. And so any wood that's used outside, fences, docks, decks, industrial applications, utility poles, railroad ties are typically treated with a chemical. Now, when it comes to its inclusion in the wood waste sector, the inclusion is inadvertent. Again, part of the reason is that untreated wood has yellowish color. CCA has a very, depending on the amount of chemical you add to the wood, it has a very light green color or a very intense green color. At the low retention level, it's a light olive color. At the high retention level, it's an intense green color. But when the wood weathers, it looks a lot like untreated wood. Untreated wood weathers to a silver color. CCA at the low retention level also weathers to a silverish type color. The high retention level wood usually still maintains its high intense green color. And so especially at the low levels, it's very easy for CCA treated wood to get mixed up with untreated wood because it looks a lot like untreated wood. And then when you have piles of wood that are this big and you're dealing with huge amounts and huge quantities and trying to sort this and identify the pieces, it's overwhelming. And it's very easy to see how easily it is for treated wood to make its way into the disposal sector. So at the time, we are on slide 11. And historically, we were very interested in knowing where the treated wood was going. It would, for example, it would end up in landfills. It could go into municipal solid waste landfills. It can go into C&D landfills. At the time, a lot of the C&D landfills were not lined. That has been changing over time. But a lot of the C&D debris recycling ends up for being utilized as processed wood, and within the processed wood, it can be used as either fuel for wood cogeneration or as mulch. So that brought us to our first project during year one at the Hinckley Center that's 20 years ago. That's a long time ago, 20 years ago, 2 decades. In our first project, and I think that's about it there, collecting some samples of wood. Our first project was to go to C&D recycling facilities throughout the state of Florida. Actually, Tim had a van full of students that went out to all the many wood recycling facilities. They collected wood samples and then analyzed those wood samples and found that by weight, 6% of that wood, that recycled material, was in fact CCA. And we were surprised. We were surprised that it was such a big fraction at that point in time. So 6% CCA by weight, on average, the processed wood at the facilities.
Was that the chemical or the weight of the wood?
It was by weight.
Of the wood? Of the
Yes.
wood, yes.
Okay. Also, in that first year, we developed a disposal forecast. And this disposal forecast has evolved over time. But the disposal forecast showed that the amount of treated wood, CCA treated wood that was being produced had increased significantly since the 1960s all the way through the 1990s. It increased a lot. And knowing that treated wood has a service life of about 25 years, we anticipate a lot of that wood coming out 20 years after it was produced. And at that point in time, we were at the upstream end of the disposal forecast. Right, this is the 1990s, we're at the upstream end, and then right now we're still near the peak, but we're out hopefully on the downstream side of the disposal amounts. That brought us to year 2, and in year 2 we were very interested in looking at the ash. Again, our study started as an ash issue. We were interested in understanding how much treated wood could you mix with untreated wood so that the ash that was produced would be would pass TCLP, and we found that 5% of a 5% mixture, 5% treated wood, and 95% untreated wood was the borderline for failing toxicity characteristics. Again, it was nowhere near land application, which is what the sugar bagasse producers wanted, but at least it wasn't, at that point at 5%, it's not, no longer, it would not be a hazardous waste. So you can go up to 5% so that it's not characterized as a hazardous waste. In addition to that, in year 2, we started our work looking at sorting. We recognized that at the recycling facilities, it's really hard to identify treated wood. And so we started working with different methods to identify the CCA. And so we played around with some stains. We also started experimenting with X-ray technologies. Also during that time, we worked very hard at looking what the impacts were during its in-service use. And during the in-service use, we actually went to decks that were treated with CCA and looked at the soils below them to understand what happens while the material is being used. We took surface cores, we took cores, and we also took surface samples. And what we found was that, in fact, CCA does impact the soils at decks, the soils below decks. The open circles here correspond to an unimpacted soil in the near vicinity. The soil collected under the deck is given by the dark circles. And again, you can see the elevated levels, especially at the surface soils, up to on the order of 25 milligrams per kilogram. This is significant because we do a lot of comparisons with the Florida soil cleanup target levels. And for residential applications, the soil cleanup target levels are used as a threshold to identify whether or not the soil needs to be evaluated more closely for potential risks. And the residential level is at 2.1, and the industrial commercial level is at 12. And so even while the wood is being used, even though the amount of arsenic that comes off the decks is very, very small, but over time it accumulates in the soil to levels that can be observed.
Can I ask a question?
Sure.
The question I have is the 0 inches. What was the date of use when the sampling was taking place?
Yeah.
5 years, 10 years, 1 year?
It was a good amount of years. We have that for the decks that we knew, but it was on the order of like 10. Yeah, on that order.
Okay.
Yeah. All right. Yeah, it wasn't a brand new deck. Thank you. We also conducted experiments where we built a deck and then subjected it to natural rainfall. It was inside of a sandbox. We measured the sand, the levels of the sand. We also measured the infiltration through the sand. And again, we found that not only did we see the impacts in the sand, but it was infiltrating through. And we saw elevated levels in the infiltrated sand to levels that were above drinking water standards, which is the threshold that's usually used to evaluate impacts to groundwater. And so not only were we able to observe it while with a new deck in the sand, you can also see the infiltration coming through.
Lynn, was that for arsenic or hexachrome or copper, all the above?
Yes, we looked at all the chemicals, all the 3 chemicals. And
all
we can
3
see,
of them.
yes, we can see. I think what really motivated the industry to change or to consider alternatives to CCA were a series of studies looking at the impacts of CCA treated wood playgrounds on children. We conducted one study, but there were other studies that were conducted as well during the period of time. And what was observed is there are CCA treated wood playgrounds. And when children play on these playgrounds, they're touching the wood. And you can actually measure before they play on the playground and after. And there were measurements where you can actually detect and measure the arsenic on the hands of the children playing on the playground. This got a lot of publicity. And as a result, I think it contributed towards a voluntary phase-out of CCA treated wood by the wood treatment industry effective 2004. So effective 2004, CCA treated wood is no longer manufactured for residential uses. It's still manufactured for other uses such as marine uses, farm uses, but it's no longer manufactured for things like playgrounds, picnic tables, fences.
Was that early 04 or late 04?
John is asking if this was early 04 or late 04. The deadline was, I think, January 1st, 2004. This voluntary phase-out occurred, I think, a year or two ahead of time. The industry was able to continue manufacturing up to 2004. Then after 2004, they were allowed to continue selling whatever they had stored up for residential. But after that, they could not make new wood for residential. Was there another question? So that leads us to the research focused on disposal of CCA treated wood. So I'm going to hand it over to Tim.
Okay, thanks, Elena. I'm going to spend a few minutes talking about what we investigated and what we learned in terms of the disposal issues associated with CCA treated wood. And again, what you have to think about is that the CCA treated wood, for the most part back then, was all mixed with other types of woody debris. There might have been a few occasions where it was managed separately, but in terms of the stuff that Danny and the C&D recycling facilities would have to deal with, a lot of times it was all coming in a mixed fashion. So you see the term leaching on the slide. Leaching tests are an integral part of what we do in the solid waste decision-making process. We're required to do that from a regulatory perspective in some instances, and also when it comes to assessing risk, we look at leaching. And we'll spend a little bit of time not only talking about the CCA treated wood, but also some of the alternatives and stuff and what we learned in terms of disposal, and then kind of ending up on some of the lessons learned with regard to the mulch and with regard to some of the sorting methods. Now, under the Resource Conservation Recovery Act and EPA, there are test procedures that determine when a solid waste is a hazardous waste. One way for a solid waste to be a hazardous waste is the toxicity characteristic, and there's something called the Toxicity Characteristic Leaching Procedure, or TCLP. As it turns out, in 40 CFR 261, which are the regulations, there's an exclusion from the definition of solid waste for arsenical treated wood. So CCA treated wood was not a toxicity characteristic hazardous waste. But some of the early research we did involved looking at that same kind of testing procedure. And what you would find is that the amount of, if you take new CCA treated wood, the amount that leached, and you can see in this graph right here, the bars on the very left are the TCLP. The toxicity characteristic concentration is 5. So you can see where 5 milligrams per liter are on this plot. Y-axis milligrams, or it's milligram per liter is the concentration in the leaching solution. What you'd find is sawdust or ground wood, which is what is required under TCLP, would exceed the TC limit. It was excluded from the definition of hazardous waste. However, it would still reach sufficient amounts to be considered a hazardous waste. And what we also found is some of the other types of leaching tests. For example, that second set of columns is SPLP. It's a rainwater leaching test. We leached similar amounts, and so it wasn't a case of where, for this waste, TCLP was so aggressive that it caused a lot to leach. It was fairly similar throughout.
And that exclusion was relatively narrow, wasn't it?
Well, it was arsenical treated wood.
But it said for certain uses, and some of the utility companies said, hey, we're not in that exclusion.
And make sure they can hear his question.
Okay, anyway.
Okay, John was asking about specifics of the exclusion. We can pick that up a little bit. Now, of course, one question is that there's not necessarily a large amount of the CCA treated wood that's being disposed of in terms of its new form. There's cutoffs that result after somebody's doing the construction project, but as that disposal forecast that Elena showed earlier really reflects, most of that's material that's taken out of service. So it's material that's been out there. It's been exposed to water or possibly other aquatic conditions. What we did one year is we went out and we collected treated wood from a number of different demolition projects or in service, and these ranged from several years to over a decade or more. And what we found is when we ran TCLP on the discarded, the older CCA treated wood, it would also fail the toxicity characteristic leaching procedure. If you see this line, actually, we did a slight modification. That line should be up to 5 milligram per liter. Okay, and so you can see at 5 milligram per liter. It just got shifted in the slide transition. What you can see is that a majority, including the new and the old, would fail the TCLP. Again, excluded from the definition, but gave you some indication of what its relative potential environmental impact might be. Now, it's one thing, though, and this has been argued a lot or discussed a lot not just for CCA treated wood, but for other types of wastes, that just because it fails in a leaching procedure where you grind it up in a laboratory, does that really mean there's a big environmental issue associated with it? We're going to focus in our discussion now about two primary ways that the treated wood, really three almost, primary ways that the wood that would contain treated wood would be managed. One of them is to go into a landfill. Another one is to be ground up and used as mulch. And then, as Helena talked a little while ago about, be ground up and used as a biofuel, or to go off and send this mixed wood as a fuel somewhere. Focusing on the landfill issue, over the years what we did is we did a lot of studies where we put different amounts of construction materials, including CCA treated wood, in simulated landfills of a number of different scales. The photograph you see in this slide, that's Dr. Jambeck, who was a student at the time and now professor at the University of Georgia. But her dissertation involved creating these large-scale landfill simulators. And what you can see in this slide is that if it was just wood, then of course you'd have massive amounts of arsenic that would leach out. These are arsenic concentrations in milligram per liter. If it was construction and demolition debris, or if it was municipal solid waste, each one of those with different amounts of wood in it, there would be less arsenic that leached, of course, because there's less material in there. But the concentrations were all still relatively large. A typical, well, the drinking water standard for arsenic is 0.01, to give you some perspective. Most landfills that have pretreatment standards to discharge their leachate, there's no one number for it, but would have an arsenic pretreatment limit, of maybe 0.05 or possibly 0.1. So these were levels of concern potentially if all that treated wood was going to end up in there. We're going to come back to that momentarily when we start talking about the alternatives, because there's some interesting things from these types of studies that give us some insight into how the alternatives might behave. This is an example in these slides of another one of these large-scale simulations. What I want to point to you is that in the plot in the upper right, what you see is these are different studies conducted by multiple students over different years, and you can see the percentage of CCA treated wood that was comprised in the waste mixture. And so, for example, all the way from 0.5%, 2%, 5%, up to 10%. And not surprisingly, then, the more amount of CCA treated wood you get into these landfills, the more arsenic that leaches. Now, we start talking about alternatives to CCA treated wood, which is what's dominating the market for residential uses these days. We'll hear more about what those different types are in a little while. Say that again?
Oh, for a while we couldn't hear you anymore. Now you're back.
Oh, okay. Thanks, David.
That last slide?
Yeah. John is asking something about the last slide.
So the top left, what was happening there?
Well, this was one of our simulations where we actually built the simulated landfills into an operating landfill. So that's an auger constructing a hole where a boring where the lysimeter was placed into.
That's different from what I'm hearing.
That's correct. When you saw it for her, hers were outside in the environment and they were strapped to the side of a leachate treatment tank. So again, the alternative dominated by copper. We'll hear more about the different types of alternatives, but when we started doing this work, copper was the primary element that was out there in the wood in terms of a metal. And not surprisingly, you see more copper leach. And so one of the big concerns was, is that going to impact the aquatic environment? But one of the things that we learned, interestingly enough, is that copper in the landfill actually gets all bound up. And so you wouldn't see the copper leach out. There's chemical reactions where that copper will precipitate out. Arsenic tends to be pretty mobile in that landfill environment, but the copper stays relatively fixed inside that landfill environment. Not necessarily the same, however, when you're talking about an aquatic environment. We also did some toxicity testing over the years where we looked at different types of aquatic toxicity assays. And I won't go into great detail on the figure, but the bottom line is that, yes, copper would leach, and the degree of toxicity associated with that copper was really a function of, number one, what's in the water, what that natural water solution is. If you have a lot of organic matter, you can actually bind or complex with some of that copper, and it's not as toxic to the organisms. And then what we found is that was also impacted by the particular type of chemical and wood product associated with it as well. So the primary concern, at least through our research with respect to the copper and a leaching perspective, is if it was in an aquatic environment, not necessarily in a landfill. It would tend to get bound up in that landfill. Again, you can see that slide that it differed depending on the type of the type of wood treatment chemical and the type of wood product. So again, what happens in the state of Florida, but this is common elsewhere, is that wood that goes into the construction demolition debris stream, whether it goes into a roll-off box at a construction site or a dump truck or a demolition site, the wood is either going to end up going to a landfill, or in a lot of cases, we have a robust recycling industry in Florida. These recycling facilities will receive this material and they'll separate different products out. Concrete, wood being probably the two biggest ones, but other products, and we'll look at some of these later on in the presentation. One of the big markets for the wood at the time we were doing the research was to grind it up and then to color it with some type of typically iron oxide type dye to create the red mulch that many of us are very familiar with, and then that would be land applied. So one of the studies we did was to go around and look to see around the state, similar to what we talked about for Thabit's study where we measured the 6%, but get additional mulch from around the state and do the testing. And what you found is that there were measurable amounts of arsenic and CCA treated wood in the mulch. That'll be one of the things as we talk about the objectives for next year that we're going to be paying a little bit more attention to because things have changed since then, which we'll talk about. This is just a photograph that is a typical example. I don't think you would see this very much these days, but back when the mulch was really first going on, grinding it up, coloring it, and then go and find that, and that would be a little game we'd play. You'd go to the parking lot, you look through the mulch, and you could find other pieces of types of wood that are not pure natural vegetation these days. John, do you have a question?
Red colorant, that iron bind the arsenic?
It had an impact in terms of that arsenic. I'll let Helena talk about that if that's something that's important. And then also, and I'll briefly introduce this and let Helena add anything she wants to, but as talked about before, the idea of how do you identify it, because if this stuff weathers over time, it's very difficult to tell. And so, Danny, you got a big pile of wood, going to it and just picking out all the CCA treated wood. It's one thing to see a big marine pile that's bright green, but it's another thing to have all of these other materials that have weathered. So how do you detect if you can't do it visually? Well, there are various stains and test kits that have been used that were discussed and described in the research that we can certainly talk more about, but if you go to the CCA research website, you'll see all that. Laser-induced breakdown spectroscopy was a technique that was tried. And then, of course, using X-ray and XRF is something that has been commonly done, both in terms of a handheld unit, and this is something that some facilities employ, and then there was quite a bit of work, and then wood recycling and folks down there were heavily involved in this, where you could add it as part of your conveyor system, have some type of automatic detection system so you could see it. And then, a subject that we might want to talk about during the discussion is how that has progressed, if at all, in terms of the industry and who might be using that at this point. I'm going to turn it back over to Helena right now.
So that ends some of the history of what we've done. It's not 100% comprehensive, but it talks a lot about the work that we've done earlier. I'd like to spend a little bit of time just talking about the types of treated wood, and a lot of my focus is going to be on the more recent distribution of treated wood that's been produced over time. And treated wood can be split up, production of treated wood in recent times can be split up into main categories of creosote, other oil-borne, and waterborne preservatives. And back in 2004, just about the vast majority of the waterborne was in fact CCA treated. But then we had in 2004 the phase out, the voluntary phase out from the industry. And then that resulted in a significant reduction of the CCA, which was then replaced with the copper-based alternatives. So essentially, after 2004, we get a big change in the introduction of the copper alternatives. Just to go back, again, treated wood, CCA, the amount of chemical that is added depends on what the wood is going to be used for. If it's above ground uses, it has a low retention level. If it's structural poles, higher level, and then saltwater immersion has the highest retention level of 40 kilograms per meter cube. Even at the low retention level of 4 kilograms per cubic meter, the amount of arsenic in the wood is significant at 1,700 milligrams per kilogram. And when you compare this value against the soil cleanup target levels, which are our reference numbers to better understand risks, the numbers are orders of magnitude higher. And if our goal is to meet the soil cleanup target levels, to meet the residential target levels, yet the amount of untreated wood that you would need to dilute out the CCA so that you can get down to the 2.1 is 99.6%. So you essentially have to have the wood free of treated wood. It has to be free of CCA. Not much wiggle room with respect to the mixing of CCA with untreated wood. You have to have essentially free of recycled wood that's free of CCA. Since 2004, we have the alternatives. This is what the alternatives look like. They look a lot like CCA. They still have the olive green color because the green is caused by the copper. And so these alternatives have the green color. And again, the alternatives include the alkaline copper quat and the copper boron azole. Within the alkaline copper quat and copper boron azole, there have been different formulations, ways of introducing the chemical into the wood, a dissolve phase, but now a more recent alternative that has been introduced by the wood treatment industry is to formulate it in a micronized formulation. So it's a nanoparticle that is then introduced to the wood. And there are questions about whether or not the micronized formulation, the toxicity of copper in micronized form versus the dissolved form. That's another very interesting question that can be addressed. But comparing the alternatives, looking at the metals in the alternatives, again, we have CCA. This is the 6.4 kilogram per cubic meter retention level, which is ground contact retention level. And the alternatives, ACQ, MCQ, which is micronized copper quat and copper azole, don't have arsenic, but they have copper, and they have more copper than CCA. So essentially what happened with the alternative formulations is they substituted the arsenic with the copper, more copper. And so the values of the copper are higher, but there is no arsenic.
Can I ask a question? Sure. Back on, you have up on the very top, not treated, and then you have levels of 2.0 on the arsenic. What, can you explain that?
The background levels of arsenic in untreated wood are on that order of magnitude. So yes, you have to essentially have, to meet the 2.1 soil cleanup target level, you're going to be right there with untreated wood. Okay, thank you. Yes.
The word fixed is used a lot, the CCA, the X-chrome, the chrome-3 reaction. Can you talk about the relative fixing or leaking of arsenic, of copper from the alternative relative to CCA?
Yeah, the word fix implies it's the chromium. When the chromium converts, it's added to the wood as chromium-6, but when it converts to chromium-3, it reacts with the arsenic and the copper and binds it to the wood. And so there's a fixation process which actually is a binding process to the wood fibers, whereas the chromium is not there for the alkaline copper quat or the MCQ or the copper azole. So there is more of a tendency of copper to leach out from the alternatives than it is for the CCA. So it's something that would be interesting to look at.
Even with the word fixed, it doesn't mean that it doesn't leak out. It's sort of stuck in the wood, right?
When it's fixed, it means that there's a process that bound it, but it still will leak out slowly over time.
So the wood acts as a reservoir.
Yes, yeah, and it sort of holds it. Thank you. So looking at the alternatives for CCA, we had to have essentially very clean recycled wood. If we are focusing on the soil cleanup target levels for untreated, for recycled wood, if we're using ACQ, the threshold for copper is higher than it is for arsenic, so we could put more ACQ treated wood in the recycled wood because of the copper toxicity, or the copper SCTL for copper is a lot higher. We put in up to 2.4% ACQ and up to 3% copper azole, with the remainder being untreated, and still meet the soil cleanup target levels. So there's a little bit more leeway when we're working with the copper-based alternatives. So that brings us to the motivation of our research. Why are we going back to all of this? This is our original diagram where we were looking at the processing of wood. And what we're learning now, and what we've, and again, Sasha, who's on the line, who explained it better than I, but there's some initiatives now to encourage the reuse of recycled wood for cogeneration, where If the wood is sorted using best management practices, this process will not be characterized as not as a solid waste, and therefore it can go to facilities that have different air emission standards. So there's still air emission standards at these facilities, but they're different than they are for a facility that burns a solid waste. And so we think that this probably is going to open up more markets for the recycling of wood as a wood fuel, for cogeneration. Sasha, are you on the line?
Yes, I am.
Yeah, Sasha, could you if you can talk into your computer and explain the non-hazardous secondary materials guidelines?
Sure. Well, can you hear me?
Yes, we can.
Okay. Basically, the non-hazardous secondary materials is our recent work stems from an original rulemaking that we needed to do to determine whether certain non-hazardous secondary materials were solid waste or not, and we're several years down the road implementing this rule, and we have a process by which industry can petition or request something called a non-categorical non-waste listing, excuse me. And so what this does ultimately, it determines if the material is determined to not be a solid waste, then it's generally going to continue to be burned in the facilities that it's always been burned in, which are regulated under Clean Air Act Section 112. However, these materials that are basically found to be a solid waste must go to a different facility that's regulated a little more stringently under the Clean Air Act Section 129 standards. So that's basically the main difference in what we've been seeking to do.
Thank you, Sasha. So there's essentially two different standards for air emissions. One is called 112, and the other one's called 129. So non-solid wastes can be regulated under 112, I believe, and then solid wastes are regulated under 129, and they have different criteria for each.
That's correct.
Thank you. So with the potential for increasing the reuse and recycling of wood, potentially for wood cogeneration, we thought, and especially given the criteria for using BMPs to sort so that the wood may classify as a non-solid waste, we thought that at that point we need to update the BMPs. It would also be useful to determine whether or not how well the BMPs are working. The FDP did develop a series of BMPs back in 2006 along with the Hinkley Center, and at this point we'd like to work on updating it because a lot has happened in the last 10 years relative to disposal, production of treated wood, and ultimately how it can be sorted.
What slide number was that?
It's 44.
Thanks.
So again, reiterating the research motivation, EPA has pending regulations that may exclude C&D wood from being classified as a solid waste if sorted using BMPs. Because of this, BMPs really need to be updated, and we also need to understand how good these BMPs are working. So this gave us the opportunity to reinitiate the study, and again, to reiterate, there are EPA regulations pending. The last I heard from Sasha was that they're probably going to be promulgated in the next month or so. I don't know if I'm correct. But again, they will be classified as non-hazardous secondary materials. Again, you have to have the sorting through BMPs, not a solid waste. And then it can be used at the wood fuel facility.
Question,
Yes.
what does the EPA consider it now, or they don't?
Again, Sasha's the one who's our representative for the EPA. My understanding, my interpretation is I don't think they really classify it. I think that's why they're
It's not on the radar.
Yeah, I think that's why this is initiated. But Sasha, can you correct me, please?
Sure, sure. We came out with the original rule in 2011, and we said that basically because C&D waste, which wood is a part of, is initially discarded, that we view it as a waste. However, we stated that we believe that if it's processed sufficiently to remove the contaminants, then we believe it be not a solid waste. So basically our most recent rulemaking has, it should be finalized very soon. We're still working with OMB to get the rule through. However, but this recent rulemaking basically lays out the concept that if you process your C&D waste stream according to best management practices, in other words, you remove the contaminants, which would include non-wood sources as well as certain types of treated wood, then we would view it as not a solid waste.
Why is that? Or why is it not a solid waste then? Why is in the process of why is it not a solid waste?
Because when it goes back to RCRA, and the statute basically says anything that is discarded, disposed of, thrown away is a waste. However, there's certain aspects that can render a material to be recycled, and as part of that, there's a set of legitimacy criteria that basically, if a material is processed and handled in a manner to meet the 3 legitimacy criteria, then we consider it to be recycled and not a solid waste. So basically, even though a material has initially been thrown away, under where we want to encourage recycling and reuse, then we have, again, this legitimacy criteria. If it's been met and a material has been processed in order to meet these legitimacy criteria, then it's no longer a solid waste.
Thank you, Sasha. Thank you.
Sure.
Very helpful. I'm going to continue on. Actually, this is the question and answer portion of the presentation as we switch over. Are there any questions? We've sort of been doing it as we go along.
What are those 3 legitimacy criteria?
Okay. Sasha, John Sherrod is asking, what are the 3 legitimacy criteria?
Sure, sure. The first one, and these are, honestly, they're borrowed from the hazardous waste side of the definition of solid waste, but they fit very well along the same lines of recycling materials. So the very first one is if you can demonstrate that material is handled as or managed as a valuable commodity. The second one is if the material possesses meaningful heating value. And third, if the material has to contain contaminants that are comparable to or less than the traditional fuel that the combustion facility would otherwise be using. So if it meets those 3 legitimacy criteria, then the material can be deemed not a solid waste.
Thank you.
Thank you very much. Any other questions? Michael?
Yeah, so one of the slides where you showed what the wood's been treated with, one of them was boron. I mean, why isn't that being used more? It's too expensive, doesn't work as well. Because I mean, the exploratory cleanup level for boron is like 17,000. So
Yeah, boron is it's an effective preservative, but it doesn't stick to the wood. It has a tendency to leach out. So they typically use boron indoors where there's no contact with the wood. If it's used outdoors, it has a tendency of just coming out of the wood.
Most of the boron treated wood was used for nailing aluminum drip plate to the edge of the house. And because if you nail aluminum to one of the copper treated ones, the aluminum disappears from electrolytic reaction. So they developed the boron treated stuff. I bought some boron treated wood, used it for a fence and a gate, and it lasted like 2 years. So it just, I mean, it's just super leaks out really fast. But it was developed specifically because of the industry uses so much aluminum drip plate around the houses, and so they needed something. And that wood generally didn't get wet because it's covered by aluminum. And so they could nail the aluminum soffit right to it, and it didn't have a problem.
There are some boron issues at landfill.
Yeah, I know that. It's mostly groundwater. And we're going to raise the groundwater level. So that's going to alleviate some. But yeah, we see a lot of boron issues at C&D sites.
Okay, so for those on the phone, the point was made that some C&D sites there are issues with boron being observed above the groundwater cleanup target level, but Michael's saying that target level is in the process of being increased pretty dramatically, which all those numbers would probably go away as an issue.
Yes.
But it goes on what John says. It's pretty reachable.
They tried treating the boron treated wood with different things to make it water repellent, with limited success. And there were, a certain number of plants around the U.S. actually started treating boron treated wood, and they colored it a special color, kind of a bluish color. And they sold it in big box stores, but it was for a specific use, and it said non-contact, and it was made really just for soffits, for attaching aluminum to it. Because if you attach aluminum to ACQ, it disappears unless you put an insulator between it.
ACQ is corrosive to aluminum.
Yeah, I bought an aluminum boat that somebody put a bunch of ACQ on. There were holes in the boat. And when they take in aluminum boats on trade, they lift them up to look and see where the boat was sitting. If it was sitting on ACQ, there will be holes back through the boat.
Are there any questions from the telephone audience?
Crickets.
I have no questions. Thank you, Helene.
Okay, thank you.
I want to know if you can hear me now.
I didn't quite understand.
This is Rick. I wonder if the audio is working on my side.
Oh, you got it working. Yes, you'd like to introduce yourself. Rick? Actually, I was gonna make a mention of you during the second part of the presentation. Maybe you can introduce yourself then.
Okay.
Okay, thank you, Rick. Okay, so that brings us to our specific research objectives, to the second part of this presentation, focused on what it is we want to do in this new research. And we have the long definitions here, and we have short definitions. Number one, our first objective is to document the amounts of treated wood and metals entering the wood waste stream. So it's essentially updating our disposal forecast for treated wood. Number two is to evaluate the effectiveness of BMPs for minimizing contamination from treated wood. So we'd like to go out to recycling facilities and measure the wood waste and see what percentage of treated wood is in the wood waste, and compare it to the 6% level that was there 20 years ago. And then we'd like to evaluate innovations in measurements and sorting technologies. So that implies updating our BMPs. So our objective number one, estimate the amounts of treated wood and metals entering the wood waste stream. This is our original disposal forecast where we took into account the various commodities, lumber, timber, fences, utility poles. We had service lives associated with them depending on what the wood was going to be used for. We then were able to forecast the disposal based on what was being produced. Given the cumulative production minus cumulative disposal, we were able to figure out how much wood was being used, how much wood was in service. And so this is the basic formula that we are using to develop our disposal forecast. And the parameters that we're going to consider in our disposal forecast, actually, we went back to a lot of the old statistics. We had the old spreadsheets, and we decided we're going to just start from scratch because the old spreadsheets were developed specifically for CCA, but we want to now look at all metals. We want to look at chromium, copper, arsenic. We want to look at it a little bit differently. And so we're revisiting the statistics, and we're going to look at the different types of treated wood and provide various service lines depending on the wood treatment. And we have Juniper and Athena that are going to give us a few words on what they've done so far and updating the forecast.
Just for those who can't see it, I'm Juniper, and I'm going to be speaking first, and then Athena will speak right after me. But basically, we're just going to go over what we've done so far, and I guess what we've been noticing through our data collection and observing trends throughout the data collection using wood preserving annual reports. So a quick little overview. I'm just going to go over the resources, basically like where we collected our data from, the findings of, I guess, what we found, and the trend analyses that we've noticed throughout our research. Okay, so our data sources. First, we looked through the American Wood Protection Association, which was formerly the American Wood Preservers Association. They're basically a nonprofit organization that was started in 1904, and they're the ones who really set the standards for wood treating, and they're very well known among wood treaters. We got the annual reports dating back to like 1909 and up to as recent as 1980, minus a couple years in between. Next, we also looked at the American Wood Preservers Institute, which is a trade industry, National Industry Trade Association. It's such a mouthful, excuse me. And they were established in 1925, and we collected data from 1990 to 1997, of course, plus or minus a few years in between as well. Then we also got some scholarly articles from LSU Agriculture Center, and we used the U.S. Department of Agriculture Forest Services for, I guess, information about preservatives used. Next we'll have our findings. That's a little breakdown. I'm going to go over the chemicals used, annual wood production, the commodity production, wood preservative distribution, and the trend analysis throughout. So for the wood preserving agents,
if you don't mind.
Say that again?
Sorry?
A little bit closer to the microphone. We're having a hard time hearing.
I'll try to speak up. Is this a little better?
No.
Sure, thanks.
Oh, okay.
Is that better? Is that better?
Try talking.
Alrighty. So for the wood preserving agents, we had a breakdown throughout the history and how they separated it. First, we have our oil borns, which are basically they use oil as the carrier to bind or mesh the chemical to the wood. Some examples would be creosote, which is a category of carbonaceous compounds, and it usually has like antiseptic as well as like anti-rotting properties. Next, we have petroleum and various chlorinated phenols, and they're all part of the oil-borne. Creosote is very widely used, or has been widely used, especially in the past. So it actually separates itself into like its own little category throughout our trend analyses, and we'll explain as we go along. Next, we have our waterborne. So what makes waterborne different from oil-borne is that it uses water as the carrier to fixate these chemicals to the wood. And some examples would be a lot of the ones that Dr. Scholler and Dr. Townsend have mentioned, so CCA of every type, so any copper-based ones, a lot of the chromated compounds, as well as any arsenic salts. Now, one thing too is that waterborne, they usually use these on softer woods, so the oil-borne is usually on harder wood, and it kind of just, there's a huge difference between throughout, and we'll see that in the trend analysis as well. Next, we have our fire retardant, and it kind of goes with the name. It's supposed to, I guess, slow down the igniting properties of fires in case they ever arise. And it basically does it in 3 different ways. It can either create a protective layer slowing down the burning process. It can also release actual like water and carbon dioxide, so that it also slows it down, I guess. And I'm sorry, it escapes my memory. Please forgive me. But there's a third way. Yes, thank you. Basically, it's a chemical cooling process that occurs, and it should also slow down any, I guess, like fires that could arise. And then the other category, now you also see other category throughout as well, and this basically is a lot of the chemicals that aren't necessarily well known or used as frequently. And also, it's like the chemicals that are kind of being tested out and they're not exactly regulated by the AWPA. So they're kind of just listed under the other section. And a majority of them are waterborne. So here, when I say preservative components, this is basically a lot of the preservative components that we've come across throughout our research. We have Woolman salt, which another name is also FCAP, which is fluorochrome arsenate phenol. Other, I guess, trade names would be like tantalum. Triolus is also one, but it's minus the arsenic. There's also osmo salts, and they just also have it under like standard FCAP. Next, we have chemonite, which is ammoniacal copper arsenate.
With the zinc.
I'm sorry?
Also zinc.
Well, so this chemonite was actually minus the zinc, but well, that's what we had in our. But it's okay. I know. Yeah, I know. You probably like know everything. I don't know if they had other place names or anything, but I don't know. I didn't know. But anyways, you know. Next, we have green salt, which is type A of CCA. And we have golden salt, and they're type B of CCA, and they're basically like different variations in the ratios between the copper, the chromium, and the arsenic. Then there's acid copper chromate, and that's also, I guess, like the trade name was Celpure, if I'm not mistaken. Next we have acid copper citrate, and that's basically like a 2-to-1 ratio of copper oxide and citric acid. Then there's also this long name, copper dimethyl dithiocarbamate. It's basically sulfur compounds with copper. Now, a majority of these have been replaced by more efficient preservatives, so some are no longer in use, but a lot of it was throughout our research. I'm going to pass it on to Nina. Go for it.
All right, hello everyone. So I'd like to elaborate a little bit on the documents that we've been using to get these statistics. So for a very long time in the 20th century, actually, can everyone hear me on the phone? I don't know how close I should hold this.
Yep.
All right, thank you. So for a very long time throughout the 20th century, the American Wood Preservation Association had produced a statistical report that comes out every year. And it's a result of their annual proceedings at a conference that they would hold every year. So this book here is something that I requested from the Interlibrary Loan System at our University of Miami. And it contains at least 6 of these annual reports. We're just trying to build up our information. We have a lot of these reports left over from all of the past research that Dr. Stoll has done, but I'm trying to fill in the gaps. So what I can do is pass this around to the people who are here and then maybe show you on the webcam if you're interested in seeing some of the numbers we've been using. So, thank you. Great. Okay, so this one was actually, this graph here was extracted from the 1970 annual statistical report. It's interesting to see general treated wood production throughout history in the United States going back to 1909. You can even see such historical events like the Great Depression taking place in the early 30s. Lack of production there. We want to update this to show even going through to today's production levels. So one way we're trying to model this is through the number of treatment plants that are in the United States. The statistical report does provide the number of reporting plants because not everyone does participate in the survey that they send. You can see a little bit of wavering in the 80s. That's when the American Wood Preservers Institute came about, and reporting wasn't so consistent from then on. But as you can see, generally there have been more plants every year in the U.S. treating wood. So preservative use, we decided to break it down into creosote, oil-borne, and water-borne, as well as iron retardants, and then the other category, which is emerging preservatives. In the 60s and before then, creosote was the primary treatment that was used to preserve the wood. Pretty sure you maybe vouch for that. I know not everyone here was around in the 60s or even practicing at that time, but that's what we found from our studies. And then moving through the years, especially in the decade of the 1970s into the early 80s, waterborne preservatives really did take over the industry. This is also the time where the EPA was forming its very basic standards and coming about with, the original regulations for chemicals being used in industry in the first place. So, interesting. Oh, John.
When did EPA issue their temporary thing saying CCA isn't regulated under the record?
Okay, so John just asked if we could give the year that the EPA said that CCA was not regulated under their organization, right? I believe it was 1976, where a lot of chemicals were also kind of umbrellaed under the, oh my goodness, Toxic Substances Control Act. I think it was 1976.
RECRA was passed in 1980, or promulgated the regulations in 79 and 80. They must have taken TSCA somehow, and probably then it would have been in the 80s, I suppose, that the exclusion would have come in. So,
okay, yeah, we can. So Dr. Townsend says that in the early 80s is when CCA was actually.
Well, I just know that RECRA, as the statute, was in 76. There were no regulations at that.
Okay. Did you guys hear that on the phone? No?
The significance of that is that prior to that exemption, people didn't like using Southern Yellow Pine because when it dries, it twists and works and stuff. And so Southern Yellow Pine was very good for taking the chemical in. And they keep it wet in the stores, and while if they put it down wet and they nail it down and screw it down, it'll stay there. But if you take Southern Yellow Pine and just let it sit out, it works like crazy. So it created a use for Southern Yellow Pine for people that want to use it. Part of that. That's what the wood guys told me.
No, that's definitely good for us to know as we start to break down into the commodity and also the wood that's used for each thing. Southern Yellow Pine works when it's wet unless it is nailed down. Okay. So what I mentioned before we went into the specific commodities and the treatments that were preferred throughout the years, this is just an example of the stacked row graph that we might be using when we go into analyzing more data. This is from 1970. Each preservative that is mentioned in the statistical report is at the bottom, and its percentage of use per commodity is what we're highlighting here. Obviously, this does not represent the actual total number or amount of this wood being produced, because lumber and timber would be probably outside if we extended the bars, and the other commodities not so much. So then I expanded upon lumber and timber specifically throughout the decade where CCA was becoming very popular, and it is the wood tone bar with the green highlight. And as you can see, this is the decade where it was proliferated and became obviously the dominating method of preservation. Once again, these are just examples of bar graphs that we intend to maybe go forward with should we find them to be useful in forecasting what's going to happen in the disposal sector. All right. This was another way we decided to look at the data, which is by preservative, what commodity was being preserved with the chemical. CCA, mainly composed of lumber and timber. Yes, okay. So before 1935, there really wasn't much use for waterborne treatment, and this graph here just kind of shows how the individual treatments were experimented with throughout the 3 decades afterward. Most of these are no longer in use, but I wanted to highlight that before that creosote, PCP, things like that were the primary treatment. And this one is pretty much a way of highlighting the history of oil-borne versus just waterborne treatments. And our data from 1984 to 1993 was taken from one statistical report, and so we think that the data changed significantly in that period and should be looked at further before using this in official documents. But I just wanted to show you how the 2 different kinds of chemicals fluctuated over time.
I think if you look at that EPA exemption from RCRA, it occurred right at the bottom, just before that graph took off.
Very interesting. So the EPA exemption for CCA occurred just as you can see the spike in waterborne.
I mean, that's right, as I recall, because that's when the use really took off. And the big box stores came out, the DIY became popular. And then the industry hired a company up in New York to facilitate the building of these community-built playgrounds. There are about 1,500 built around the country to get people used to using CCA wood.
Specifically to get people used to it. Wow.
To show that there wasn't any hazard associated with it. And a lot of the playgrounds got torn down.
Yes, I remember Castle Park, New Jersey.
They're
still there. Yeah, absolutely. I mean, depending on where you go in the country, you may still stumble upon one, but definitely where I'm from, they've been eliminated.
When the playground thing came up, it was the perfect made for local TV thing, because a reporter could buy an arsenic soil test kit for like $15 and test the dirt at their playground, and then they dig up all this dirt and replace it with wood chips. And a lot of the chipped wood would have chipped CCA wood.
All right, well, I'm so glad we're having this meeting so we can learn more about the situation and its history. All right, so I think that's everything we have so far in our experimental manipulation of the data. We're going to have to look for more information regarding especially the recent decades after the voluntary phase-out. That information is something I've requested from the interlibrary loan system at the University of Miami, and I'm pretty sure I'm going to have to go beyond that because it's been a while since I've sent in those requests and I haven't gotten much of a response.
Are you able to just access the AWPI yearly, reports?
Okay, so we're not able to access those reports from the AWPI without paying a significant amount of money to get them. However,
it's the Southern Forest Products Association. It's the one that's.
Are they? Southern Forest Products Association might also be helpful, but I think they're also quite expensive to get the documentation.
You have to be members of both, correct?
Yes,
correct.
so first you have to be a member, and then you also have to buy each individual report. I mean, eventually, I don't know if we'll resort to that, but that is an important question to ask. So, are there any other questions or suggestions on where we might take this?
Well, Elena is a member of the IRGWP, and I'm a member too. And they have extensive libraries of information about treated wood. The International Research Group on Wood Preservation. They have they got tons and tons and tons of papers, and every year they hold a big annual conference somewhere around the world, and they have a huge reservoir of papers and databases.
That's a good
source to know about as well.
We need to get to that.
Thank you. All right. Well,
I think we'll switch over now.
Yeah, we'll switch into objective 2.
Thank you, guys.
Thank you.
Thank you.
Thank you.
Okay, I'll go ahead and introduce objective 2 real quick, and then I'm going to hand it over to Kim to talk about some of the details. If you remember from earlier, it was in the late 90s when we did that study and went around the state and collected samples and got that 6% CCA number. You just remember Thabit's picture from where he was one of the one of the,
And that was a darn good study, if I may say so.
it was excellent. So what we're really talking about as part of this objective is doing something similar, but now that those BMPs are out, to see what has changed since then. Just briefly look at this equation right here. The idea is if we want to know the mass of CCA treated wood that is currently being disposed in any one of these particular disposal sectors, we know the amount of C&D going to that sector, the fraction of wood that's in there. And then if we have some estimate of the fraction of CCA that's in that wood, we'd be able to try to get that. So we have a couple opportunities here. Number one is to evaluate the BMPs and how well they're working. And then number two is to get some numbers that we can compare to the disposal forecast that you heard Juniper and Athena and Dr. Solvier will talk about in a little while. Just real quick, I wanted to share, especially for some of our C&D recycler folks here, is that, you know, we did some estimates fairly recently for the Construction Demolition Recycling Association of how much construction and demolition debris is actually out there. This is our estimate right now from at least the composition from the United States. And of course, what you find is there's huge amounts of concrete. A lot of that doesn't end up at all your facilities, though, because it ends up at mobile crushing plants or other facilities. If you look at wood, if you look at the overall amount of C&D debris in the United States, you might talk, you know, less than 10% or so. That's just because the mass of the concrete is so great. But that's still many, many tons of wood that are being disposed of or being produced. We have estimates for Florida now. They're not shown here, but once that's finalized, that'll be something that we'll be able to use as part of this. The state of Florida does track the amount of C&D that's produced every year. There are reports that go to DEP that estimate or provide how much was generated as well as how much was actually recycled. Some of these data don't capture all the sources of material, but they probably do a pretty good job with respect to the amount of wood that's being produced out there. So what we're going to do is we'll use some of the more recent estimates of construction demolition debris amounts, the amount of wood that's in construction demolition debris. Also, I think looking at some of the sources where it's going to in terms of what's going to landfills maybe versus the different markets associated with the recycling operations. But then ultimately the question is if we get a sample of this wood that's ground up and mulched at these facilities for the different end markets, how do you analyze what fraction of that is CCA? So Kim, come on up and you can walk us through the methodology that we use.
Good morning, I'm Kim Strickland. I'm a new graduate student working with Dr. Townsend. I've been a Gator for about 2 months now. So anyway, Dr. Townsend introduced this equation, and our focus is going to be just on the last term, the fraction of CCA wood in the C&D waste stream. Oh, we already talked about this. So our methodology is going to be very similar to what was done in 1998. Hopefully we will do that study justice with our sample collection methods. We plan on going back to the same 12 C&D facilities that were used in 98. If some of those have been closed, we're going to get as close to as we can, so we're consistent. We plan to take samples from shredded wood piles. We're going to fill up 35-gallon containers, and we're going to take at least 20 grab samples from each wood pile, so we want to get just as consistent and homogeneous as we can with our samples. We are going to take XRF measurements when we take our grab samples, and I know that is going to be a bit of a challenge because the wood is shredded, but I was actually talking with Dr. Ursula earlier, and we just want to make sure that we get our method down with our first grab. That way we can be consistent. So if we have to take 5 measurements or 10 measurements per grab, then we just make sure we do that with everything. Then we will take our samples. After we collect them, we will size reduce them. We will ash them at 550 degrees C. And then we will analyze for chromium and copper. And arsenic is volatile at a very high temperature, so when we ash our sample, that's where we're going to use chromium as our indicator. Not doing anything.
It might go away. Just keep on talking.
Oh. So again, we have our equation. And what we'll do is we'll take our chrome concentration that we get. So in the numerator, we have our field samples. And then we will subtract the chrome concentration that we will get from untreated wood. We're going to use southern yellow pine for that. And we'll do the same methodology as far as sample prep and analysis. And then we will divide that by what we know is the CCA concentration, or I'm sorry, yes, the chromium concentration in CCA treated wood, and then account for the chromium concentration that we get in our untreated samples. So that's how we will come up with our CCA fraction. And of course, things have changed a little bit. We have copper-based alternative wood treatment products. So we're also going to do that calculation, and that equation is actually a little bit more robust. So there's a little shortcut here. I can write the equation out if you guys would like, but it's really very similar to what we do for the chromium and the CCA treated wood. We will take our copper concentrations, we will subtract out the copper concentrations in our untreated wood samples, but then we're also going to account for the copper that is found in our CCA samples. So again, that equation is just a little more robust. We'll just take that out of our equation as well. And then when we get all of our sample results, to wrap up, I guess, task 2, we will compare what we actually get in our measurements and to what is predicted from task 1. And that will bring us to research objective 3, and I'm not sure who's. Does anyone have any quick questions? Oh, yes. Sorry.
There was some work done by Dr. Jake Huffman and Jeff Morrell on loss of CCA from hosts that were in the ground for 40, 50 years, something like that. And there have been other studies by these folks and by Dr. David Stilwell on loss of CCA chemical from wood and use. And I think it'd be interesting to kind of take a look at, how much arsenic's coming into the country, how much of it's in the dirt, and how much of it's in the wood.
Well, for arsenic, I know when we prepare our samples, that's what we're using as our indicator. And I know we have our estimates of what's, I guess, naturally occurring as well in our untreated wood, but I agree we'd be very interested to see just what's in the soils as well. So.
Yeah, I mean, because, the wood acts as a reservoir, and each time it rains, it washes it off the wood, and then solubilizes the chemical in the wood that comes to the surface. That's how it works. And so there's been a fair amount of work on how much is lost during the service life into the soil beneath decks and docks and those kinds of things. And I think it'd be a big step.
Okay.
Maybe the microphone's too close.
Okay.
One other idea is that when you find out how much arsenic is there, you could actually estimate how much would end up in air emissions or ash if that wood were taken to the combustion facility.
And there are papers on that.
Well, in their specific cases.
So are you asking if there are specific?
No, I'm just making that point there.
There was a bunch of work done in Australia on combustion of CCA and how much arsenic goes up the stack and how much stays in the air.
Yeah, maybe we could connect after. I'd like to talk a little bit more about that. What I'm hearing is an overall comprehensive mass balance, not only in the water, but also include the soil, what goes up across the atmosphere. So I think we'll see what we can do with the model. And actually, this time around, last time around, our model, we did it in Excel. But this time around, we're going to do it in MATLAB. And that gives us a lot more flexibility in being able to program and do much more with it than doing it as an Excel spreadsheet.
In what?
In MATLAB? MATLAB.
John, we can teach you MATLAB if you want.
We'll set the code.
Inside joke.
Yeah. Okay.
I'm still working on Excel.
Okay.
Well, I'd like to switch gears a little bit and talk about objective number 3, which is focused on innovations in sorting technologies, which translates to updating the BMP. We need to document the innovations so that we can update the BMPs. The BMP is going to include our updated disposal forecast. I see some of you have been looking at the old BMP, the 2006 one that was brought, I think John or Tim Vincent brought. So that will be updated. The old BMP did not acknowledge copper-based alternatives, so we're going to be putting more information on the copper-based alternatives, and also including more work that was done looking at new technologies for sorting. A copper stain was developed. We have done a lot of work on XRF. And also thanks to Florida Wood Recycling, Gene, I think you may be on the line, and also to Rick of Austin AI, we had a full-scale system operating to test separation of treated from untreated wood. That was at the far right. It was at the Florida Wood Recycling facility. And we'd like to include results from that operation along with cost estimates. How we're going to do more updates on what's already been done. We plan to interview C&D recyclers, so we will be calling and interviewing and learning more about what you think works and what doesn't work. And we want to include some of that and a summary of the interviews from C&D recyclers. We also plan to contact XRF manufacturers. I've already spoken with Rick, who's the manufacturer of the automated XRF, and it was an amazing conversation because so much knowledge has been learned. The work that we did at Florida Wood Recycling was almost a decade ago, maybe 8 years ago. And he's learned so much about what works, what doesn't work. And it's just fascinating, the possibility that it may be doable. One of the conclusions from our conversation with Rick is that rather than focusing at the C&D recycling facilities to do the sorting, have a secondary sorting or a backup sorting over at the wood cogeneration plants. Because there you have the volume coming in at the wood cogeneration plants, and then there can be some additional backup sorting there to separate treated from untreated wood. And Rick emphasized the benefits of working with the mulch versus the big pieces of wood. It was really hard to separate those big pieces, develop a conveyor system that would separate one from the other. Rick, are you on the line?
I think so.
Oh, Rick, can you introduce yourself, please?
Sure. Well, first I have a question. When did the Gators get their own time zone?
When did the data get their own time zone? Oh, the Gators get their own time zone.
Yeah, look behind you.
I think our clock is wrong.
Oh, you've seen the clock on the, oh yeah, I was looking at that too. I was thinking we were way behind. You want to say a few words about yourself, Rick?
Hey, Rick, speak up.
Yeah, it slows down.
Say that again?
Have to stand by. Yeah, but you're seeing something that very few people know. They have their own time zone.
They need it.
Okay, Rick, do you hear us? Do you hear us?
Yep, you're back. Yeah.
Okay, do you want to?
I was having a conversation with all the other online participants. Every once in a while, we lose the video.
Okay, yeah, I'm sorry about that. Yeah, we tried our best to get the video and the audio working, and I understand that it wasn't perfect.
No worries. We had fun without you.
Okay. Okay.
Yeah, I'm with Austin AI. We basically make online sensor-based sorting equipment. We work with all sorts of technologies, not just XRF. Some of the more recent systems we've developed are LIBS-based for light element sorting in scrap metals, and we're working now with terahertz to do black plastic sorting online, X-ray transmission and other induction sorting, things like that. So we're a little more broad-based than just XRF, but clearly the lesson learned over the last 15 years by us is that automated sensor sorting has to be done involving three very distinct aspects of the sorting. And one is the material and the feeding of the material into the sensor belt or chute or whatever. Then it's the sensor section itself, and then finally the diversion of the material. It's clear that if you want to do mass quantities, viable quantities of any material, it's imperative you get the material into a like kind, size, and flow. And again, working with 4x8 sheets of plywood or something like that, and then trying to get 2-inch pieces of wood processed, it's too much of a challenge for an automated system. We are at the point now where with our XRF, we're making in the time domain of 10 or so millisecond determination of concentration of various flag elements. For example, we can sort titanium from Inconel machine chips down to 3 millimeters using X-ray analysis and capable of doing 1,000 to 2,000 pounds an hour, even a very small material. So the world has changed, as Helena has alluded to, and we're very comfortable that the aspect, really, I don't think there is an economical viable quantity at any one C&D recycler site. I think it's going to make more sense at the consumer site, where many tons an hour would need to be processed. And that's basically at the point where if it's not rendered ready for incineration or burning, it will be done there. So that's where any final grinding or wood chipping or whatever you do to process it to get it into the furnace.
Rick, you're a little bit muffled. You're a little muffled. You're a little muffled.
Okay.
But what we understood on this side is that Austin AI has a lot of different sorting technologies. XRF is one of many. I think for CCA, XRF works really well, but we'd like your insight on that. You also emphasized the need to get everything to the same size. So using wood of different pieces of different sizes is not good for sorting. If you get it all like mulched up and then sort it, that would be more beneficial. You also mentioned, for everybody here in person, you also mentioned that at a C&D recycler, it's probably not economical there, that ideally it should be moved to the cogeneration plant, correct?
Correct on all accounts.
Okay. All right. Thank you, Rick. Thank you.
You're welcome.
So in addition to the XRF manufacturers and other sorting technologies, he mentioned lids, we mentioned lids as well. We plan to also interview representatives from cogeneration facilities. The benefits of the work that we're doing, again, we're going to document the life cycle of treated wood. We're going to evaluate the effectiveness of current BMPs, address C&D wood waste and non-solid waste, update the guidance document, and ultimately this project will help us improve recycled wood quality, which is really what we're after. Our communication strategy, ccaresearch.org, we're in the process of updating that and setting up another web page. We will be participating in solid waste meetings. We plan to publish in scientific journals and also in the lay solid waste journals, and then also host tag meetings. And our timeline is as follows. Again, we will be updating our disposal forecast through the spring, going out sampling through the spring, through the early summer as well, updating the BMPs, and then we have a series of deliverables that include our progress reports, of which one I have to submit by the end of this month, and we have our tag meetings, and then our final report. So I'd like to ask, thank you everyone, and are there any questions?
Well, Helena, this is Gene from Florida Wood Recycling.
Hi, Gene.
Hi. I don't have any questions. You were very thorough along with everybody else. The only thing I have to say is thank you again for setting up this meeting. It's very informative. I think it sets the goals and objectives that we all want in the industry. Along with that, I'd just like to say you're always welcome, and your team of researchers are always welcome. Harvey wasn't able to be here. He's in Vermont. So I'm conducting the meeting on his behalf, and you're always welcome here. That's what he wanted you to know. And the only other thing I could say in saying goodbye is I saw Tim on the camera, and we go back several years, you and Tim and I in the studies. You said decades to decades. The only thing I can say is he's lost a little hair. I've lost a little hair, but you don't look a day older than the first time we met.
Yeah, well, you can't see the gray on the screen, unfortunately, but I am a little grayer. But thank you. And Jean, thank you, and Harvey, for your incredible support. You've sponsored 2 projects on your facility, allowed us to get access to your facility. As others here, Danny, for example, we're going to be visiting your facility, Fernando, tomorrow. So I want to thank Jean, Harvey, everyone who has really supported us throughout the years on this research. Thank you.
Many blessings to everybody.
Is that it?
I think, are we done? Well, thank you. Thank you. We're going to close up the go-to meeting. I think we're done about 10 minutes early. So thank you, everyone, for sticking it out, and I hope the audio wasn't that bad. So, thanks again.
You're very welcome. Thank you. Goodbye, everybody.
Bye.
Bye-bye.
I disconnect the line.
So Danny, I just want to know your thoughts on doing this all over again?
Well, yeah, probably, but I'm thinking about this stuff.